Lesson 7, velocity and other rates of change. I mentioned yesterday at the end of our notes, velocity. It's a derivative, right? Which is why this is coming up. This is an application of derivative type day. Okay? Derivatives we often talk about in relation to physics because I mentioned yesterday, velocity is a derivative of position and acceleration is a derivative of velocity. So, okay. I think I just kind of explained that first paragraph, didn't I? Mm-hmm. If you've taken a physics class, this will seem familiar. And your job is to help the rest of us get the physics portion of it. Yep. So, the big ideas of straight line motion will be revisited many times throughout our course with increasing difficulty. So, we've been using two different notations for derivatives. Lagrange's notation is the one you guys prefer. Or, well, no, I don't know what you guys prefer. We haven't been doing this long with, but it's the one I prefer. It's the one students usually prefer because it is the prime mark, right? So
and
Lagrange is exactly. That's the one that it's easy to write, isn't it? It's the most common modern notation, named after Lagrange. The original notation goes to Leibniz, and his is the one that is the dy dx.
You got right.
Okay. What?
You got right.
Okay.
Oh.
Okay. Now, the advantage of the Leibniz notation. It helps with the units, okay? Because since it mentions here, derivative is a division process, unit will always be the y-axis units divided by the x-axis units. When I always read it, it's a derivative of y, so it's a derivative of that equation, because it's y equals when we take derivatives, right? With respect to x. So dy dx means it's an equation that's y equals, and x is the variable within the equation. So if we see like dy dt, that's an equation that is y equals, but then instead of having x's in it, it has t's in it. So that just determines which variable you're taking the derivative with respect to. Okay, so suppose that s equals f of t gives the distance in feet of an object from a fixed point as a function of time t in seconds. What is the common term for ds dt?
Velocity.
Okay, so this would be the first derivative of position. And the first derivative of position is velocity, right? So s of t, s is a common variable for position. It's telling you position because it mentions distance, right? Okay, we're talking how far we move along, so that's a position. But then ds dt, that's the change in position over a course of time, and that is velocity. Okay, describe the following notation in real-world terms. So ds dt, and this is our little evaluation bar, evaluated at t equals 4.
Velocity at 4 seconds. Or speed at 4 seconds.
We don't want to throw the word speed in. Speed is different.
Okay.
Speed is different. Well,
Acceleration.
no, this is only first derivative. Okay.
I have no idea what velocity is.
Distance over time. Or position.
Distance over time is acceleration.
That's distance over time squared.
This is position.
Yeah. When we talk meters per second, we're talking velocity. When we talk meters per second squared, we're talking acceleration. Okay? So, when we're talking, and we'll talk more later. I don't think it comes up today at all. But there is, when we talk calculus, there is a difference between velocity and speed. Okay? I mean, yes, they relate, but yet there's a difference. Not that I want to go into it today,
The
but
thing that drove me crazy though was Mr. Kevin would interchange those and use them, and I drove me crazy because I was like, I don't know.
I'm guilty at times.
One does it, right?
What?
So,
One had a vector,
Yeah, one has a vector.
They
Yeah.
still use it.
one has, I would say, I think of one has a sign and one doesn't. So, okay, now, So, what did I hear?
Velocity at time.
Okay, velocity when time equals 4.
Yeah.
Now, instead of velocity, I say, because did I write? I don't have velocity written at this exact moment, in this exact one. But what else have we used to describe a derivative?
Who's
Like
the
tangent line?
Mm-hmm.
Your position,
Are you talking about
your point.
like that problem that we had? It was people per
There's slope.
minute or
I'm trying to think. I can't. I'm trying to clue you on how to get there. I'm not looking for slope of the tangent line. Okay, I've heard all of that. That's not what I'm looking for. How do I? So we have found.
The limit.
A-Rock,
We have not AROC though.
I-Rock.
IROC.
Okay, that's
Okay, so AROC. See, here's the difference. AROC is over an interval, whereas IROC is at an instant, at a point, right? So IROC being instantaneous rate of change. So this is your IROC of an object in what would be our label,
Feet per second.
feet per seconds, when t is 4 seconds. Okay? So I mean, it's all stuff we're putting together. So if I write IROC, do you know what I mean, or should I?
Yeah, but I wrote it.
I'm gonna write it out too, but. So the point is, when we talk about a derivative, it's instantaneous rate of change, yes? So this is the IROC of an object in feet per second when t equals 4 seconds. Okay. I don't know if I wrote out feet per second, but whatever. Okay. Thoughts on the real world meaning of f prime of 4 equals 18?
When time equals 4, the instantaneous rate of change in feet per second of an object is 18.
Jeez.
Say that again.
Instantaneous
Slower
change
took
at
the
40
top
is
and
18.
reworded it for the bottom.
So it gives you the answer. So 18 feet per second.
Okay, so when t equals 4 seconds, so at time 4, yes?
Yeah.
What do we know?
It's going 18.
Okay, you could say instantaneous rate of change is 18. Now, it's not going 18 feet. This is a derivative, so the instantaneous rate of change is 18 feet per second. Or on this one, I actually have the velocity is 18 feet per second.
So IROC and velocity interchange.
In a given situation, yes.
Oh.
Okay.
Because velocity could also be 8.
Yeah, I was going to say, I've got to be careful here. So, I have mine written down as when t equals 4 seconds. The velocity of an object is 18 feet per second. I don't really have room to squeeze this in, but I was going to try.
Oh,
The comment I've written in my notes, and I'm sure there's a reason I put in here at the time, but, okay, we're just kind of talking about, velocity versus speed, and that'll come up later, but this is a positive velocity, okay? A positive velocity tells me that that object is moving, what'd you use?
like,
Well, I have away from a fixed point. Okay? So it's moving away from a fixed point.
Like that one with the pendulum where it's happening to the thing and it's like,
Yeah.
Oh my god, I have like no memory.
So positive velocity, what was I writing?
Right now.
Tells us the object is moving away from a fixed point.
Everybody feels it. It's like every single day.
Yes. I'm with Mario.
You're sitting there and you're like,
What are you spelling?
just
And
staring.
I will tell you guys, I am a math teacher, not a science teacher, which means this is not one of my best strengths. Okay? Doing the math behind it, perfect. But I sometimes, teachers have weaknesses too. And I'll be honest, there are times that I get my connections crossed and confused, and you have to bear with me. But
Just like I'm not a science fan.
I'm not English now. Visualizing it
I'm
is what
great at econ. I
makes
have no
me
idea why.
so angry.
okay,
So easy.
I did not know this was a big question until last year, doing these notes for the first time. But did Neil Armstrong step off the lunar module and pick up a moon rock from the surface of the moon on July 20th, 1969? If he did, see, and I had no clue this would even a discussion until last year. And my students were like, yeah. And I'm like, okay. If he did, scientists say that the rock would have a velocity, 24 meters per second, or about 86 kilometers per hour. The height of the moon rock can be modeled by the function given here.
What does it mean the rock has the velocity? Did it move forward?
Did somebody move? Is
No,
the rock
it's
floating around
moving.
the air?
There's no gravity.
So it is moving.
So things are,
Okay.
there's no gravity to hold things down.
Okay.
So things are floating.
Okay.
So the rock is,
Just moving.
I'm using the word floating because that's what I think of things doing when there's no gravity. But it's saying it has a velocity of 24 meters per second. So to me, that's a little more than floating. But
Yeah.
I can't say I've ever been up in outer space. So,
Same. Well, maybe neither has Neil Armstrong, so you never know.
there we go. Okay. A. Find the velocity and acceleration of the moon rock as a function of time. So, what do I need to find here?
Height at t seconds. I think. I don't know.
Maybe you should.
Well, that one's just find the velocity. So let's find the velocity, I guess.
How do I find velocity?
But you have to square root it.
You have to do the derivative of the
Go back
height
to what we
equation right
talked
there,
about yesterday.
because that's position. Height is position, so you're just doing the derivative of st.
Bottom of page 135. S of t is your position function. V of t is your velocity function, which is equal to s prime of t. Okay, so in order to find velocity, we are finding s prime of t. So I'm finding the derivative of the position. Height is a position. So, what's that derivative?
Negative 1.6 t plus 24.
Okay, I'm going to write it the other way around, but derivative of 24t is 24 minus 2 times 1.8, so 1.6t. Are you with me?
Yes.
And if you wrote it the other way, more power to you. Find velocity and acceleration. So, acceleration, what do we know about acceleration? It's the second derivative of position, which makes it the first derivative of velocity. Good news is we've already found the first derivative, so you just continue and find the second derivative, yes?
Yep.
And that is? Negative 1.6. Okay. Um, I don't have a label written on velocity, but I think I did on acceleration just because it's one value. What's an acceleration label? Meters per second squared. Whereas velocity, if we wanted to label that, would be just meters per second. Now, notice what it did say. Note, the acceleration is the acceleration of gravity on the moon. So that's saying that that is the acceleration of, like, that's gravity on the moon for everything. Okay?
That's saying that the moon is drawing you like 6 meters per second squared. You're moving towards it.
It's not drawing you towards the moon because there is no gravity.
It's just the gravity
It's-
in general of the area.
Yeah, I don't.
This is so
This
confusing.
is.
Well,
It's kind of like
the moon is not probably the best example either to start with, though.
the
but-
Earth would be so much easier because it.
Exactly. Earth has, so to offset it, Earth has positive acceleration. Well,
It has a
No.
negative acceleration. Negative.
I'm thinking.
That's fine.
Okay, never mind. Not gonna go there. Because, yeah, I'm realizing that's not gonna help
By
my.
the end of the year, we didn't even talk about negatives and positives. We just left them all out
Okay, so
completely.
Earth being negative
Yeah.
9.6 meters per second squared.
9.8.
It's 9.8.
Or 9.8?
I say in math we use 9.8. I don't know what they know past 9.8.
What's 9.8?
Earth's acceleration. Negative 9.8.
So that means that
Meters per second.
that means that
You
the
just know that.
Is it saying that
Yes, I had that engraved in my
Yeah.
brain.
the moon's
Last year.
1/6
Yeah.
of what the Earth is, so if you multiply that by 6, you get 10.6.
So it's not that exact relationship, though.
No.
Okay. B. How long will it take for the rock to reach a maximum height?
What?
You tell me.
Google.
Okay. Think in terms. If we look, okay. So, position. What's this position function? A graph of?
Hyperbola.
Parabola.
Parabola. not
Parabola.
That's like not parabola.
Specifically, a. Are you with me on the upside down parabola? The rainbow. Okay. Now, how long will it take for the rock to reach the maximum? Where's the maximum?
The top.
Top.
At the top here, yes? Now, we don't know what that maximum height is, do we? Because if we knew the maximum height, I could set my position formula equal to that maximum height, and we could solve for t. But we don't know that. What is going on here when it hits that maximum height?
You start with this.
Okay. Your slope is 0. It stops. Yes, both are valid points. Both lead us to the fact that slope is 0, which is what in this situation?
Here. Acceleration.
No.
Velocity.
Velocity. Okay, velocity is first derivative, yes. So velocity is more along the slope. Velocity is similar to speed. Okay, not exactly here, but so what's happens, when you hit a turnaround point, your speed goes to 0. Your velocity goes to 0. So we are looking at setting our velocity formula equal to 0. Velocity was 24 minus 1.6t equals 0. So 1.6t equals 24. And t is whatever 24 divided by 1.6 is. I have 15 written down. 15 what?
Seconds.
Seconds. Okay. Continuing along here. So that was how long did it take the rock to reach a maximum height? 15 seconds. C, two different questions here, one at a time. How high did the rock go?
You put back to your room.
Plug what where? Huh?
Plug 15 into
The negative.
Not negative 15, just 15. Time is 15. How high did the rock go? We want to look at the position, because that's my height, that's my max height, right? So we want to look at the position at time of 15. So we're going to find S of 15, which is 24 times 15 minus 0.8 times 15 squared. Do some math.
So did we miss putting the T in on like the A and B? Did we don't have to have the T there? What?
Hmm?
I'm just confused.
We were taking a derivative.
Oh,
So we obviously didn't have to put in a T.
okay. Well, obviously it wasn't that obvious.
I was just
Okay, so on A, we were finding derivatives. So we had the given function. They didn't ask us to find the velocity or acceleration at a certain point, which might be what you're thinking. I'm not sure here. They just asked us, in general, velocity and acceleration as a function of time, which means I'm looking for a general equation. This one, they asked for maximum height. So one thing you need to learn is, in that terms, maximum height, that's going to happen when your velocity goes to 0. So that was taking my velocity equation and setting it equal to 0, because that's when it's going to not really stop, but stop for an instant and turn around type thing. This one, so the first part, how high did the rock go? Well, it reached its max at 15 seconds.
To get to the original.
So we're putting 15. We don't want to put 15 into velocity, because the velocity is going to be 0 at that point. We want to know the position, so we're putting it into our height formula. Now that's 180 what? Meters. And no one's doing the math for me, so that means no one has their calculators out. Wow, how things have changed since the beginning of the school year.
I would totally
So-
have my calculator if it wasn't at home.
Okay. Now, the other question. When did it hit the ground?
30 seconds.
Do we put it? We put it in. We put 15 in that equation into the velocity equation. Right.
If you put 15 into the velocity equation, I'm going to find velocity to be 0.
You're right.
30 seconds.
I don't know.
What's the parabola? And your middle is 15.
Okay, but what if we haven't done part B?
I am curious on how to do this, so I don't.
Okay. So what do you know when the rock is on the ground?
Velocity.
Velocity is 0.
Okay. Well, we've already dealt with velocity of 0, and all that gave me was the max. I did a different plan. What about position? If the rock is on the ground, the height of the rock is 0. So when did it hit the ground? It hit the ground when S of t is 0. So we're taking S of t, 24t minus 8/10 t squared, and putting it equal to 0. On this, when I say do some math, both terms have t's. So factor out GCF. My brain is struggling with that negative t squared term, so I think I would factor out a negative t. Actually, if I wanted to, I see an 8. I know it's a 0.8, but I see an 8 and a 24. If 24 divides by 8, 24 can also divide by 0.8. Now, do you have to factor the 0.8 out? No. But what I factored out on mine is a negative 0.8t. if I reverse my pieces here, negative 0.8 t squared divided by negative 0.8 t is t. 24t divided by negative 0.8 t is minus 30. Now, officially, just to review the math, set each factor equal to 0. So officially I have negative 8/10 t equals 0 and t minus 30 equals 0, which means officially I have what answers? 30 and 0, yes? Does it make sense that I have two answers?
Yes.
Mhm.
Yes.
Yes, because the height of the rock is 0 when it starts and when it ends. What did this question ask? When did it hit the ground? Well, we're assuming they want 30 seconds. Okay. These relationships are ones we have to know, folks, okay? Ones we have to know. Oh, Lordy. Okay.
Yep.
Moving along. We there? Got some basics? Okay. In our last lesson, we have defined y equals st as the position function of a particle or object. Wow, can't read. However, y equals f of x can be used to represent many different quantities such as amount of rainfall, temperature of yams, volume of a cone, people infected by a virus, or other situations. The derivative will help us discuss how these quantities change at any given moment in time. So take a break from physics for the moment.
Oh, thank God.
Okay, in other words, it's still physics related, I guess, in a way, but we're not specifically talking position, velocity, acceleration. Okay, we're looking at, okay, what do these expressions mean? What do these labels mean? So, suppose W of x is the daily quantity of water in gallons required by a palm tree of height x feet. Explain the meaning of each expression in a complete sentence, including units. So this is take the math and put it in words. Take the calculus and put it in words. So, okay, let me point out. W of x is the daily quantity of water in gallons required by a palm tree. And x is the height measured in feet, right? That defeated the purpose of underlining when I underline like everything. Okay. It happens. You guys are guilty too at times. You start underlining, it's like, oh wow, I just highlighted like everything.
Mm-hmm.
W of 25 equals 38. Put this in words as to what do 25 and 38 represent? How do they connect?
The palm trees.
38
And they
gallons
got 38 gallons.
is a daily quantity
Okay.
required by a 25-foot palm tree.
Okay. A 25-foot palm tree requires 38 gallons of water per day. So there's no derivative, there's no inverse, there's nothing. It's just plug in 25, you get out 38. So 25 feet palm tree requires 38 gallons of water per day. That's easy type, right? I put it in words, I'm just translating it. I got my labels in there, right? What's 25 represent? What's 38 represent? Okay. W negative 1 of 38 equals 25.
It's the same thing as the question.
Yes and no. Okay, so what does this negative 1 represent?
That's the inverse.
Okay, so this, if you recall, is the inverse. And to an extent, I mean, what does an inverse do? An inverse switches our input and output, right?
Mhm.
So now it's making the 38 the input the 25 the output. When we state it, we usually state it a little backwards. So like this one, I stated it as it's a 25-foot palm tree requires 38 gallons of water per day, right? Whereas here, trying to get my wording, well, or when a palm tree requires 38 gallons of water per day, what do we know? The palm tree is 25 feet tall. That's kind of the idea of the inverse. Is it still relaying the same information in a way? Yes, it's still the same labels and everything. It's just a matter of your input is 38. So what is 38 gallons of water saying? The palm tree is 25 feet tall. And so my wording here, when a palm tree, oh my lordy, requires 38 gallons of water per day, the palm tree is 25 feet tall. Okay. Start thinking about C. What is C? It's a derivative, yes? Well, it's a derivative. Think about it as a rate. Think in terms of rate of change here. What'd you say? Not an hour. Well, okay, but it's because it's a rate of change, we're saying that it's changing at a rate of 6 gallons per day. Sorry, my labels are getting all confused. Okay, so this one, the input is a 25, right? So when the palm tree is 25 feet tall, the amount of water needed daily is, because it's a positive 6, I'm going to say increasing 6 gallons at a rate of 6 gallons per foot. Wait, is that supposed to be day or foot?
Because as it increases in height, it increases in the amount of gallons of water it needs to have.
Okay. Okay. When a palm tree is 25 feet tall, amount of water needed daily is increasing, again, increasing because it's positive, increasing at a rate of 6 gallons per foot. And we said increasing because it was positive. Okay? It's rate of change. And we will pick up there tomorrow. And we need to make good progress tomorrow.
Hi. Remember if you